Let's talk about the next point, which is a satellite. Okay, so what is a satellite? So anything that revolves around a planet, right? So like moon is the natural satellite. Okay, and we project some artificial satellites also for the communication purpose. Okay, so for a circular orbit, let's suppose this is a satellite, this is moon or any artificial satellite. It is revolving around earth, okay, or any planet. It can be planet earth or some other planet, right? Okay, so other planets can also have satellites. So the satellite revolves around earth, suppose, okay, at some height h above the earth's surface. Then we know that centripetal force is provided by what? Gravitational force, right? Centripetal force is provided by the gravitational force. So we can say FCP is equal to GMM divided by R square. Okay, so FCP is mv square upon R, and that is equal to GMM divided by R square. Okay, then you can cancel out m, and this R will get cancelled out with this R. So you get V square is equal to GM upon R, GM upon small r, right? What is small r? Small r is capital R plus H. Okay, so V square is GM upon R. Therefore, what is V? V is the speed with which the satellite revolves. This is also called as orbital speed of a satellite. This is also called as the critical velocity of satellite. So what is critical velocity of a satellite? It is square root of GM over R. Okay, R is equal to R plus H, capital R plus H. Small r is equal to capital R plus H. So you can always substitute that. So what is critical velocity or the orbital speed of satellite? It is square root of GM divided by R. This thing is clear, everyone? Okay. All right, very good. So then you can, as we discussed, that this is very handy substitution. GM is equal to G times R square. Okay, so we can substitute that, or GH multiplied by small r square. So if you substitute that, you get V is equal to, okay, in place of GM, we substitute GH into R square. Okay, so then this R gets cancelled out with R in the denominator. So V is equal to square root of GH into R. We get another formula for the critical speed of satellite. Okay, so VC is equal to root of square root of GH into R, right? So this is at some height h on Earth's surface, or near to Earth's surface. Okay, not on Earth's surface. Satellite revolves, suppose, near to Earth's surface for a small height. We can say that VC is nearly equal to square root of GM over R, and that is nearly equal to, you can say, square root of GR, right? This is clear? Yes, no? Okay, good. Then the time period of a satellite. We want to find out the formula for time period of a satellite. So we have this speed with which it revolves in the circular orbit. It is given by square root of GM divided by R, and you can substitute that speed in circular orbit is equal to 2 pi R divided by T. T is the time period, right? Then you square both sides, so you get 4 pi square R square, right? Square of 2 pi R is 4 pi square R square divided by T square is equal to GM or R. And then you rearrange this, so you move this R on this side, T square on this side, GM in the denominator. Then you get T square is equal to 4 pi square R cube upon GM. Okay, and from here, see, this is Kepler's third law, right? So square of the time period is directly proportional to what? Cube of the semi-major axis, that is cube of average radius. So we get that from here. Okay, so t square is proportional to r cube, and therefore what is t? So take square root of this. So t is equal to 2 pi square root of r cube by gm. Okay, so we should remember this thing. T is equal to square root of r cube. Sorry, t square is directly proportional to r cube, and also this thing, also this formula, that t is equal to 2 pi square root of r cube by gm. Right? Is this thing clear to everyone? Okay, so you need to remember this formula also, not just t square is proportional to r cube. Okay, all right. Then let's talk about a geostationary satellite first. What is time period of a geostationary satellite? So suppose you want some satellite to be stationary with respect to some position. Okay, suppose this is Earth and this is your satellite. It's revolving in this orbit. It revolves like this. Okay, and suppose you are here. You want to, suppose you see the satellite, it's there. Okay, it is there today, and I mean it is there today morning, it should be there today evening. Okay, it should be there tomorrow, day after tomorrow, day after day after tomorrow, right? So it should be at the same position with respect to you. Then that satellite is called as geostationary satellite, right? If position of a satellite does not change with respect to any point on Earth, then that satellite is known as what? Geostationary satellite. See, what is geostationary satellite? So geostationary satellite is a satellite whose position does not change with respect to Earth. And what does that mean? So if Earth rotates about this north-south axis, okay, its time period is 24 hours, then satellite should be there at the same position. It means that it must also revolve with the time period of 24 hours only. Right? Yes, no? Then only it will remain stationary with respect to the Earth, any point on Earth. Okay, so then its time period must be equal to 24 hours. That's the point. That's it. There is nothing else. So if time period is 24 hours, you can put that t is equal to 2 pi square root of r cube by gm. This is your formula for the time period. Then t is 24 hours. It is fixed. Okay. This small r can be written as what? Capital R plus h. Okay. And you have cube of that, right? So t can be written as 2 pi square root of r plus h cube divided by gm. Okay, and then r is fixed, gm is fixed, time period you have fixed, you want it to be stationary with respect to Earth, and that means h should be constant. Okay, so h is fixed too. Is this thing clear? Yes, no? Because everything else is constant, you get a fixed value of h. So geostationary satellite cannot revolve around Earth from any height. Okay, its height is fixed. Okay, so that is height of the geostationary satellite is this much, 35,786 kilometers. Okay, 35,786 kilometers. Now you don't even need to remember this number, right? The height of geostationary satellite is this much. So from this topic, we just need to remember that time period of geostationary satellite is 24 hours. That's it. Okay, and its height would be fixed. So there is nothing much in this topic. Okay, even if it is deleted, not deleted, doesn't make any difference, right? Okay, all right. So this is geostationary satellite. So then, so we have talked about the speed of satellite, time period. Now let's talk about energy of a satellite. Okay, what is the energy of satellite? What is energy? Total energy is just sum of potential energy and kinetic energy, right? Total energy is just sum of potential energy and kinetic energy. So what is potential energy? Minus of gmm divided by small r. Okay. What is kinetic energy? It is half of m multiplied by v square. Okay, it is half of m multiplied by v square, right? So then you put v square, okay, v square is equal to what? Gm upon r, right? Because v is square root of gm upon r for a revolving satellite. V square is just gm upon r. Okay, if you put that, then what do you get? This thing is minus of gmm divided by r is the potential energy, and what is the kinetic energy? It is half of gmm over r. Okay, you remember this thing also and this thing also. What is potential energy of a satellite? Minus of gmm over r. So we know what is potential energy. We should remember what is the kinetic energy too. It is half of gmm over r. Okay, so then if you add it up, what do you get? You get total energy is equal to minus half of gmm divided by r. Okay, total energy is just equal to minus half of gmm divided by r. Is this thing clear? Everyone? Right. And now here is an important point, because there were direct question based upon this thing. So total energy is just half of the potential energy, because potential energy is minus of gmm divided by r, and total energy is minus of half of gmm divided by r. So total energy is just half of the potential energy, and if you see, total energy is minus half gmm upon r, kinetic energy is plus half gmm upon r. So total energy is negative of kinetic energy. Okay, so total energy is half of potential energy and total energy is negative of kinetic energy, right? This thing is clear to everyone? Okay, and that means what is kinetic energy? You can substitute total energy is half of potential energy. Okay, so potential energy is equal to minus 2 times of kinetic energy. Okay, so you get it from there. Potential energy is just minus 2 times of kinetic energy. Right, this thing is clear to everyone? So we got relation between total energy and kinetic energy, total energy and potential energy. And also kinetic energy is equal to minus half of potential energy. Okay, so let's remember this. Kinetic energy is equal to minus of negative of total energy. And what is total energy? So total energy is half of potential energy. So kinetic energy is just minus half of, okay, this negative sign is there, minus total energy is half of potential energy. So kinetic energy is minus half of potential energy. Okay. All right, this thing is clear, everyone? Right? Very good. Then next is binding energy. What is binding energy? Binding energy is energy required to make any body free from Earth's gravitational influence. Okay, energy required to make any body free from the Earth's gravitational influence. How much of energy should you give to a body to make it free from Earth's gravitational influence? Okay, this thing is clear. So right now, suppose the total energy of a satellite, revolving satellite, is how much is it? minus of half of gmm upon r. This is the total energy of a revolving satellite, but it's negative, right? You want to send it to infinity, so how much of energy should you give? So at infinity, suppose you give some energy, okay, so it already has some energy, that is its total energy, it's minus half of gmm upon r, plus you give some energy and it escapes, okay, it escapes Earth's gravitational bound, so it reaches infinity, so there its energy becomes zero. That means how much of energy do you need to give it? So its energy is minus half of gmm upon r. If you give plus half of gmm upon r, then what will happen? It will escape, it will be able to escape, right? This thing is clear. Okay, everyone? Good. So binding energy is just negative of the total energy. Okay, binding energy is just negative of total energy. And how do you give that energy? So you give that energy in terms of the kinetic energy only. Okay, but now for a revolving satellite, this binding energy would be just equal to the kinetic energy. Okay, binding energy would be just equal to kinetic energy. Now see, there are too many relations, you might say, okay, but it's not at all difficult. Total energy is half of potential energy. You need to remember this. Kinetic energy is negative of total energy. Total energy. You need to remember this. Okay, for a revolving satellite. And the kinetic energy, because it's negative of total energy, and total energy is half of potential energy. So kinetic energy is minus half of potential energy. Right? Okay, so this is true for a revolving satellite. And this is always true that binding energy is negative of total energy. This is always true that binding energy is negative of total energy. Okay, this is clear, everyone? Right, very good. So then now suppose satellite is revolving around Earth and you want it to escape. Okay, satellite is revolving around Earth and you want it to escape from Earth's gravitational bound. So you need to give it some energy. So you give it in form of the kinetic energy. So kinetic energy of escape must be equal to what? It must be equal to its binding energy. That is energy required by the satellite to escape from Earth's gravitational bound. Okay. So kinetic energy of escape is half of m into v square, and that's equal to half of gmm upon r, and then you get v square is equal to gm upon r, because this half and half will get cancelled out, m gets cancelled out, then you get v is equal to gm upon r. So therefore ve is equal to what? V square is gm upon r, v is equal to root of gm upon r. Okay, so the critical velocity, you know, the velocity with which the satellite revolves around Earth, it is square root of gm upon r. If you give it that much, okay, same amount of more velocity, it was already revolving around Earth with some speed, gm upon root of gm upon r. If you give it same amount of kinetic energy, it will escape Earth's gravitational bound. Okay, so this thing is clear, everyone? Okay, so now in case of a revolving satellite, the escape velocity is just equal to critical velocity. Okay, escape velocity is just equal to what? Critical velocity, or escape speed is equal to the critical speed, you can say. Okay, is this thing clear to everyone? right? Very good. So escape speed is just equal to the critical speed in case of a revolving satellite, right? Then what is escape speed on Earth? So here you should not get confused. What is escape speed for satellite steady, which is steady on Earth surface? It is square root of 2 gm over r. Okay. And what is the escape speed for a satellite which is revolving closer to Earth's surface? Let's say the square root of 2 gm divided by r. Sorry, square root of gm over r, right? So if satellite is steady on Earth's surface, then escape speed is square root of 2 gm over r. If satellite is revolving, okay, closer to Earth's surface, then escape speed is just square root of gm over r, right? This thing is clear, everyone? Okay, so escape speed of a satellite which is just resting on Earth's surface is root 2 times of its critical velocity. Okay, so this is, it is satellite or it's any body which is resting on Earth's surface. What would be the escape speed? It is square root of 2 gm over r, right? This thing is clear? Yes, no? Okay, so there is this relation between the escape speed, okay, this is crucial, escape speed on Earth and critical velocity of satellite. So it is v is equal to square root of 2 vc. But if satellite is revolving, okay, then escape speed to that satellite and its critical speed, it is same. Okay, is this point clear? Right? Escape speed of a satellite which is resting on Earth is equal to what? Root 2 times of the critical velocity of a satellite. Critical velocity is velocity with which the satellite must revolve, okay, at any in any orbit, we can say. Okay, so escape speed on Earth for a satellite resting on Earth's surface is equal to root 2 times of the critical velocity near to the Earth's surface, we can say. Okay, but if satellite is revolving, already revolving, not resting, then its escape speed would be equal to its critical speed. Okay, for resting satellite it's root 2 times critical velocity. For revolving satellite, v is equal to vc, right? Okay, yes, no, remember this thing. Okay, good. And then now suppose this is a rocket, okay, and you project the rocket like this, exactly perpendicular to Earth. The rocket is vertical. Then we know that escape velocity is equal to square root of 2 gm divided by r. Okay, now suppose a rocket is launched from the same position but not vertically. If it is launched like this, in this direction, okay, at this location only, if it is launched, let's say at this location, if it is launched like this, Now what would be the escape speed? Will it be same? Will it be different? Okay, it should be same, right? It should be same. Okay, because escape velocity, if you say escape velocity, it is said, it is called as escape velocity also. It's a misnomer. It gives us impression that it's a vector quantity, right? It's not a vector quantity. It's the amount of speed that has to be given. Okay, so there have been questions like this. If rocket is launched vertically upwards, okay, escape velocity for that rocket is v. Okay, now if the rocket is launched at an angle of 30 degrees, let's say, with respect to horizontal, what should be the escape velocity? And they nicely give, okay, option like this. So suppose it is launched at an angle theta, then they gave v sine theta. Okay, one option would be that. V cos theta would be another option. Another option would be equal to v, right? So what's the answer? Answer is it should be same. This thing is clear, everyone? So now let's solve some problems based upon satellites. The escape velocity from Earth's surface is v. The escape velocity from the surface of another planet having a radius 4 times that of Earth and the same mass density is. Okay, what's given? Radius of that planet is equal to what? 4 times the radius of Earth and its mass density is same. So density is same. Density of the planet is equal to density of Earth. This is given. You want escape velocity. So what's the formula? V is equal to square root of 2gr, right? So let's use gp rp because we want escape velocity at that planet. Okay, so that is equal to square root of 2 times what is g? It is 4 by 3 pi r rho g, right? And r is radius of the planet, okay, r suffix p, and rho is also density of the planet. So let's put rho p multiplied by you have rp. Okay, so everything else is same, just this radius is different, right? So you have rp times rp means rp square, and you can take it square root. So it is rp multiplied by square root of 2 times 4 is 8, right? 8 by 3, then it will be pi rho p g, that's it. And this is the escape velocity for the planet. What would be escape velocity on Earth? Escape velocity on Earth would be just equal to what? Similar formula, but it will be r square root of 8 by 3 pi rho multiplied by g. Okay, and then if you compare this with this one, you can substitute this rp is equal to what? It is 4r. rp is equal to 4r. Substitute that. So 4r square root of whatever, it's 8 by 3 pi rho times g. Okay, because rho p is equal to rho, and then this thing is equal to the escape velocity from Earth. Okay, you can say it is ve, escape velocity from Earth, and therefore vp is equal to what? It is 4 times of v, right? This is the answer. Okay, this one is clear? Yes, no? Okay, all right, good. Let's see next one. The time period of a geostationary satellite is 24 hours. So they have told that time period of geostationary satellite is 24 hours at height of 6 RE. Okay, and RE is radius of Earth from the surface of Earth. Then the time period of another satellite whose height is 2.5 RE from the surface of Earth will be. Now there is, see, nothing no more information about a geostationary satellite is required. This is normal question based upon satellite. Okay, so even if we know nothing about geostationary satellites, still we can solve this one, right? So time period of geostationary satellite, so let's say T1 is equal to 24 hours and its height H1 is equal to 6 times radius of Earth. This is given. Okay, and then you have H2, height of second satellite, 2.5 times of radius of Earth. Let's call it R only. Okay, and what would be its time period? What would be its time period? Okay, so we know T is directly proportional to, or T square is directly proportional to R cube. So let's put that. So T2 by T1 square is equal to R2 divided by R1 square. So that is equal to R plus H2. Oh, it is cube, sorry. R plus H2, right? R2 is R plus H2 and R1 is R plus H1. We have cube of that. Okay. Then let's put the values of H1 and H2. It is R plus H2 is 2.5, right? H2 is 2.5. Okay. And R plus H1 is 6. Okay. It is 2.5 R and this is 6 R. And you have cube of that. So then this is R plus 2.5 means 3.5 R and this is 7 R. Right. So 3.5 divided by 7 is 1 by 2. So then you have 1 by 2 cube. That means it's 1 by 8. And this is T2 by T1. T2 by T1 square. Now take square root of that. So you get T2 by T1 is equal to 1 upon square root of 8, that is 2 root 2. Move T1 on that side. So what do you get? Therefore T2 is equal to T1, which is 24 divided by 2 root 2. Okay, so 24 divided by 2 is 12. Then 12 can be written as 6 times 2, 6.2, 6 times 2 divided by root 2 is what? 6 root 2. Okay, 6 root 2 is the answer. It's option A. Right? This one is clear. Okay, there is nothing in this one, right? Okay, you just need to compare them. Okay. All right, let's see next one. A remote sensing satellite of Earth revolves in a circular orbit at a height of 0.25 multiplied by 10 raised to 6 above the surface of Earth. Okay, so this is remote sensing satellite and it revolves in circular orbit at a height of this much. Okay, if Earth's radius is 6.38 multiplied by 10 raised to 6 and g is equal to 9.8 meter per second squared, then the orbital speed of satellite is, so height is given, okay, radius of Earth is given, then g is given. So okay, so what formula should we use? We want orbital speed, so it is given by gm divided by r plus h, right? This is the formula. And then what is gm? Okay, gm is equal to, you can say gr square because g is given here, right? Gm is equal to gr square. You have gr square divided by r plus h. Okay, and that is g is 9.8 multiplied by r square. Now this height is small, we can say. Okay, so radius of Earth is 6.4 multiplied by 10 raised to 6, right? This is 6.4 multiplied by 10 raised to 6 and this is 0.25. So plus 0.25 means it will be 6.65. So 6.65 multiplied by 10 raised to 6. Okay, and this thing is 6.4 times 10 raised to 6 square. So you can cancel out 1 10 raised to 6 out of that, and then I think we should cancel out this with this, okay, right, this with this. So 1 6.4 will remain. So 6.4 times 9.8. So let's take 6 for simplicity. 9.8 and let's make it 10. Okay, so 10 times 6 is 60. So you have root of 60 multiplied by 10 raised to 6, round figure. Okay. So then what is square root of 60? So square root of square root of 64 is 8, right? Then it means that it is less than 8 because it's 60, okay, but it's definitely greater than 7. Why? Because square root of 49 is 7, okay, and this is round figure, so it will be nearly 60, right? So something between 7 and 8, okay, 7 point something, let's say 7.5 multiplied by 10 raised to 3 meters per second, and that is option C. Okay, so is this thing clear? Yes, no? Okay, so this is, we are doing round figure here, lot of round figuring. Okay, all right. So I think this should be the answer. You can check it, right? Because the options are very close. Yeah, I think this is the answer. Okay, let's see next one. A satellite S is moving in elliptical orbit around the Earth. The mass of the satellite is very small compared to mass of the Earth. Okay, a satellite S is moving in elliptical orbit around Earth. The mass of satellite is very small compared to that of mass of Earth. Then the linear momentum of S remains constant in magnitude. Does it remain constant? The linear momentum? Yes, no? No, because linear momentum, okay, it is P, which is equal to mass times velocity, and velocity changes in elliptical orbit. Okay, if satellite is close, if satellite is close to the planet, then what happens? The velocity increases, right? If it is away from planet, velocity decreases. So v is not constant, that means momentum is not constant. The acceleration of S is always directed towards the center of Earth. Is this one correct? The acceleration of S is always directed towards the center of Earth. Is this one correct? This one is correct, right? Acceleration is always directed towards the center of Earth. Okay, it is centripetal acceleration. Right? So this one is correct. Let's see next one. The angular momentum of S about the center of Earth changes in direction, but its magnitude remains constant. So we know that this is a radial force. That means torque is equal to 0, because torque is equal to what? Rf sine theta. Okay. So if suppose this is this is Earth and the satellite is revolving in elliptical orbit, let's say something like this, then this is the satellite, this is satellite. Okay, so what would happen? So this is the force and radius vector will be directed. Okay, radius vector means its position vector will be directed from the position of planet towards the satellite, and force acting on the satellite would be in opposite direction to that. So therefore theta is equal to what? Theta is equal to 180 degrees. Okay, so we had seen this earlier also. So you have Rf sine of 180, right? Sine of 180 So sine 180 is 0, that means torque is 0. If torque is 0, then the angular momentum is constant both in magnitude and direction. Magnitude does not change, its direction also does not change. So this is incorrect. They say that the direction of angular momentum changes. Okay, so it is definitely not correct. Okay, the total mechanical energy of S varies periodically with time. So we know this, that total mechanical energy, that is sum of the potential and kinetic energy, remains constant. So it also does not change. Okay, so this is incorrect, this is incorrect. So what is the answer? It's option B. Right, this one is clear. Okay, good. Let us see next one. A geostationary satellite is orbiting the Earth at a height of 5r above the surface of Earth. This is similar to the earlier one. R being the radius of Earth, the time period of another satellite in hours at the height of 2r from the surface of Earth is. Okay, this is similar to the last one. So time period of geostationary satellite is what? It is equal to 24 hours. So T1 is equal to 24 hours. Okay, so we just need to remember this thing. Okay, then H1 is equal to 5r and H2 is equal to 2r. Then what is T2? Right? So you have T2 by T1 square is equal to R2 by R1 cube. Okay, and what's that? So this is T2 by T1 square of this is equal to R plus H1, this is R plus H2 square, not square, cube, divided by R plus H1 cube. Okay, so that is equal to, what is H2? So H2 is 2R. So this is R plus 2R divided by R plus, what is H1? H1 is 5R, R plus 5R, and you have cube of that. So this is 3R divided by 6R, means 1 by 2, 1 by 2 cube. Oh, once again the answer is same, right? So this is 1 by 8. Okay, this is T2 by T1 square. Take square root of that. So you get T2 divided by T1 is equal to 1 divided by 2 root 2. Move T1 on that side. So which is 24. 24 divided by 2 root 2 is what? 12 divided by root 2, that is 6 root 2. So T2 is equal to 6 root 2. Okay, so they have changed the heights in the way that the answer comes out to be same. Okay, so T2 is equal to 6 root 2. Right, this one is clear. Okay, it is similar to the last one. Okay, good. Then let's see next one. If V is escape velocity and VO is orbital velocity of a satellite for orbit close to Earth's surface, then these are related by, tell me. What's the answer? It's option D. Okay, escape velocity is equal to root 2 times of the orbital velocity, right? Okay, let's see next one. The radii of circular orbits of two satellites A and B of the Earth at 4r and r respectively. The speed of satellite A is 3v, then the speed of satellite B will be. Okay, radii of circular orbits are given and you want the ratio of the speeds, right? This is simple. You know that V or Vc is equal to what? Square root of Gm divided by R. Okay, so let's take V1 is to V2 and Gm would be constant. It's equal to it is inversely proportional to root of r, and that's why it will be r2 divided by r1. So v1 is 3v and we want to find out v2, and that is equal to r2 upon r1. So r2 is r, r1 is 4r, right? r1 is 4r, r2 is r. So again r gets cancelled. So this is 1 by 4, root of that is 1 by 2. We have 1 by 2 on right hand side, so it's 3v divided by v2, and therefore what is v2? v2 is 3v times 2, so that is 6v. That is 6v. Okay, so it is option B. Right, that's the answer. Okay, so this one is very simple, right? Actually all questions are very simple, some are conceptual. Okay, let's see next one. A ball is dropped from a spacecraft revolving around the earth at a height of 120 kilometers. What will happen to the ball? It will fall down to earth gradually. Okay, so ball is dropped from a spacecraft. Spacecraft is revolving around the earth at a height of 120 kilometers. Okay, what will happen to the ball? So let's suppose this is earth, right? And there is a spacecraft which revolves around earth. This is the spacecraft, and a ball is dropped from here. So this one. Okay, so it will fall down to the earth gradually. It will go very far in space. It will go very far in space. Okay, it will continue to move with the same speed along the original orbit of the spacecraft, and it will move with same speed tangentially to the spacecraft. Okay, tell me which one is correct? Is it option D? Anybody else? Option C, it will continue to move with the same speed along with the original orbit of spacecraft. Yeah, that is correct. Why? Because see, when it's like, suppose you are in a bus, okay, and bus is moving with some velocity, right? So if you drop a ball from that bus, what happens? That ball also moves with the same speed, okay, in this direction. But because of gravity, okay, because of Earth's gravitational acceleration, okay, acceleration due to gravity, okay, what happens? It takes trajectory like this, it falls on Earth. But basically when you drop it, due to its inertia, it had same speed, okay, as that of the bus. So here also this ball will have same speed as that of the spacecraft. And why is spacecraft moving like this? So at this point the spacecraft has velocity in tangential direction, right? The velocity of spacecraft is along the tangent. Okay, why does its trajectory take a curve like this? It's because of the gravitational pull due to Earth, and it will be same for the spacecraft as well as the ball, right? So if spacecraft revolves in circular orbit because of this velocity, okay, and because of the gravitational pull, the ball will also revolve in the circular orbit. Is this thing clear, everyone? Yes, no? Right, so answer is option C. Okay, good. Then let's see next one. A satellite of mass m is orbiting the earth of radius r at a height h from its surface. The total energy of satellite in terms of go, okay, g0, the value of acceleration due to gravity at earth's surface is. Okay, so tell me what is total energy of satellite? Anyone? Total energy of a satellite is equal to minus half of gmm divided by r plus h. Okay, and then you have gm equals to gr square. They are calling it as g naught. Okay, so let's put that. So you get minus half of g naught r square divided by r plus h. Okay, and this m is there. So the option B is the answer. Okay, so Bhanu found the answer, right? This one is correct, and this one is very simple, right? Okay, so I can see that there are only one or two questions, conceptual questions, where we need to think. Otherwise, all other questions are formula based. Okay, let's see next one. Two satellites of Earth, S1 and S2, are moving in the same orbit. Okay, in the same orbit. The mass of S1 is 4 times the mass of S2. Which one of the following statements is true? Okay, which of the following statements is true? The potential energies of Earth and satellite in the two cases are equal. Okay, are they equal? Two satellites, they have masses? No, they are not equal. Very good. Okay, mass of S1 is 4 times that of mass of S2. What is the potential energy of a satellite? Gm times m minus of gmm divided by r. This is potential energy, right? If mass of satellite changes, potential energy changes. S1 and S2 are moving with the same speed. Is this one correct? Not correct? So if they are moving in the same orbit, means they should move with the same speed, right? Yes, that's correct. Because what is the speed? Speed is equal to square root of gm over r. Okay, this capital M is mass of Earth. It is not mass of satellite. Okay, so it is same for every satellite. And what is r? R is the radius. So radius of orbit is same. That means speed would be same, right? So speed of a satellite does not depend on its mass. Okay, speed of the satellite does not depend on its mass. So option B is correct. Okay, then the kinetic energies of two satellites are equal. They are not equal, of course, because Ke is equal to half of m into v square. Though the speeds are same, masses are different, so kinetic energies cannot be same. Then the time period of S1 is 4 times that of S2. So is that correct? So again, speed is same means time period will also be same. Speed and radius is same. So time period is same. So this is also incorrect. Right? So it's option B only. Okay? Right, very good. Alright, let's see next one. For a satellite moving in an orbit around the Earth, the ratio of kinetic energy to potential energy is. Okay, tell me. What is the ratio of kinetic energy to potential energy? So kinetic energy is kinetic energy is half of gmm divided by r. Potential energy is equal to minus of gmm divided by r. So if you take the ratio of these two, kinetic energy is to potential energy, then you get minus half, right? Gmm and r get cancelled out, and you get minus half. Okay, but there is no negative sign, so they want only the magnitude. So if minus half is also there in the options, that would be the answer. But here there is no minus half, it is plus half only. So that's the answer. Okay, so they are just asking about the magnitude. Right, this thing is clear. Okay, everyone. Right, good. Let's see next one. The satellite of mass m is orbiting around the Earth in circular orbit with velocity v. what will be its total energy? So remember, total energy is always, tell me, option D. Yeah, very good. Total energy is negative of kinetic energy. Okay, so that is minus of half of mv square, right? This one is clear. Okay, good. Okay, so a satellite is orbiting just above the surface of earth with period t. Okay, if d is the density of earth and g is the universal constant of gravitation, the quantity 3 pi divided by gd represents. So this is from NEET 2023. Okay, time period of a satellite is given by what formula? T is equal to 2 pi square root of r cube divided by gm. And what is r? R is equal to r plus h, right? So if satellite revolves very close to the earth's surface, just above the earth's surface, means h is negligible, h is small. Okay, h is very small compared to r. Then what we can do is we can just neglect h. So if we neglect h, what do we get? We get 2 pi, this is not h, okay, this is pi, 2 pi square root of r cube divided by gm. And then now you want this capital G, it's there, GD. Okay, so how can you write this GM? So if you remember, we can write GM equals to what? A G is already there, right? So you just need to convert this mass. Mass can be written as what? Density times volume. Okay, mass can be written as density times volume. So density, they are calling it as D. Okay, you want density in the denominator, right? Here. Okay, so mass can be written as density times volume. Let's substitute that. So if you substitute that, you get r cube divided by g multiplied by m. M is written as density multiplied by volume. Volume is 4 by 3 pi r cube, and then that r cube and r cube gets cancelled out. Okay, and what remains is 3 goes to the numerator. Okay, so t is equal to 2 pi multiplied by square root of you have 3 times r cube got cancelled, no, 3 times, okay, 3 times nothing, 3 times in denominator you have g d, what else, 4 gd. Okay, then you can take square of this, so t square is equal to, then what do you get, 4 pi square multiplied by 3 upon 4 gd. This 4 gets cancelled out. Okay, oh, there was this pi, no, this pi is also there, and pi gets cancelled out, right? 4 gets cancelled out, pi gets cancelled out, and then what do you get? 3 pi divided by gd, 3 pi divided by gd, and that is your answer, right? So what is that? It is t square. Okay, it is t square. Is this thing clear?